Welcome everyone. So this is the course on D modules and representation theory. So it's a fascinating subject, and in a couple of weeks' time, Milicic will arrive. So this is Dragan Milicic from Salt Lake City, and he is a real expert on D modules and representation theory. So basically, he'll be kind of leading the course once he arrives. But I'm not sure he'll give lectures every week. So lectures will include myself. So it's Milicic. Also, next week I will not be here, and Alan Stapleton has very kindly agreed to give the lecture next week. And myself, and potentially we can convince Alex to give a lecture up to Alex as well.
You see that present.
Okay. So there's various, don't expect the same person every week. The other thing is, so important things. Here is the website of the course. So on this website are the three sources of literature that would be the most important references. Namely, there is this wonderful little book. This is by Kashiwara called D modules and Local Calculus. It's this wonderful little book by Kashiwara, D modules and Local Calculus. There's also these notes of Bernstein called algebraic D modules. And then there's much longer notes of Milicic. So these are the three references for the course. Also, there's this quote that I wanted to read to you from Nietzsche. He says, "For I approach deep problems like cold baths, quickly into them and quickly out again." Okay? And I think that if you look at, for example, this book of Kashiwara or the notes of Bernstein, he very much treats, they very much treat the subject like a cold bath. And so, it's really not an easy subject. It's like algebraic geometry plus extra difficulty. So one has to get used to that. Yes, so there's the website. It has the literature on it. It also has the link to a Slack channel, which I would encourage you to join if you're interested in taking part in the course. So if there's questions. So I like Slack because you can have a discussion a little bit like in a room where someone says something, and then if you feel like you've got something to say, you can just reply, rather than emails, which is like much more directed person to person. So this is another experiment. We'll try to use this Slack channel for discussion exercises. The final thing is I'm trying a slightly different format for this course, which is to have something like between 1 hour and 1.5 hours of lectures, and then like actually exercises. And so each time I'm going to try to have exercises that we're going to try to discuss as a group. And you're welcome to leave at any time, but if you're actually trying to do the course, I'd encourage you to try to do the exercises. Okay, so let us begin. Is there anything else from an administrative point of view?
Can we take a source for credit?
So I was just having a discussion with Oded earlier, and it seems that the requirement that you take courses for credit as a PhD student is now optional again.
Okay.
So
be careful, it might be starting this year and people start going.
yeah. So if we can do it like last semester, which
If PhD students need the course of credit, you can definitely use it.
yeah, if PhD needs, you can definitely use this. Yeah. Any more questions? And also, so there's some people from UQ who I've seen them join the Slack channel and welcome on Zoom. And Daniel is very kindly taking care of Zoom, so please feel free to ask questions and we will try to answer them. And IFS principals are here too, so any interruption or additional explanation is welcome. So this will be a somewhat very introductory lecture, just about why we care about the modules from the perspective of differential equations. So D modules, and please also yell at me if my writing becomes too small, is the algebraic study of linear partial differential equations or linear differential equations. And it's a subset of a subject called algebraic analysis. So one way to approximate this is like, imagine that you're very, very good at algebra. What can you say about differential equations? Okay. So just as an example, so this example will run for some time. So we consider a polynomial differential equation. A polynomial differential equation, so we have like something like the sum a I z d to the I times f equals 0. I'm going to call it star. And so these AI are polynomial functions on C. And d to the I is shorthand for d to the I. So this just d to the I just means differentiate items with respect to z, and we assume so I goes from 0 up to n, and we assume that an is on z. So we have a linear ordinary differential equation of degree n. Now, remark. The first remark is that solutions form a vector space. So if I had, for example, the differential of f all squared, then that would no longer be a linear condition. I would no longer have a linear partial differential equation. So it's very important to remember that this whole theory of D modules is about linear differential equations, linear PDE. So solutions form a vector space. And the theorem of Cauchy so let B x epsilon denote an open ball at x of radius epsilon. So Cauchy's theorem says that if Bx epsilon does not intersect the zeros of An, then the vector space of solutions to star would be except one as dimension n. Okay, so here's C. And then we have these are the zeros of our. So these are just polynomials, yeah? They're not of any specific degree, so this can have 100 zeros. Zeros. Yeah. And then this differential equation may have no solutions on the whole space, but as long as I choose a ball, which is disjoint from my zeros, I have m linearly independent solutions, and then these form a basis for my solution set. So I just want to give some examples because these are absolutely essential. So these 4 examples, I think one should keep in mind for the entire course.
Really?
Yeah.
So the solutions that we're looking at, can we assume that they're like real analytic? Like, can we assume that they're power solutions?
Yes. As a vector space of analytic, so the vector space of solutions has dimension n and consists of analytic functions. But that's a complex analytic function. And that's very important. So notice that, so for example, Bernstein's notes are called algebraic demodels. So he's always working in the category of algebraic varieties. He's using polynomial differential operators. But when you take solutions, you should always consider solutions in analytic functions. You know, it's very easy to write down that. We'll write down a very simple polynomial differential equation in a second that has no probabilities.
And that theorem is reasonably obvious if you assume everything is power solutions.
Yeah.
Because then you can see it.
Exactly, yeah, you just get a, like, you know, it's like an unknown thing. Exactly. Yeah. So, df equals 0. Okay, so now solutions are simply constant functions. It's c times the function that's 1 degree. Okay, so this is probably the easiest example. And then we can take d minus 1 f equals 0. So equivalently, this is saying df equals f, and here the solutions are multiples of the exponential. Scalar multiples of the exponential. So in both these examples, the solution exists everywhere because my leading coefficient is has no zeros. Now we get the slightly more interesting example. So z d minus a half equals 0. So, you know, because I don't do differential equations, because I don't do D modules every day of my life, whenever I restart the subject, it takes me a little while to process this. And then, you know, is equal to yeah. So roughly speaking, if I think about this as some kind of polynomial, this is taking its degree down by 1, and then I'm upping the degree again, and I want to get a half. And so you can say that also this tells me that I'm going to have a problem with 0, potentially. And you can see that on any bx epsilon which doesn't intersect 0, this has a basis of solutions given by c times some choice of the square root function on that one. Okay. But note that there's no global solution. This is a funny one that is incredibly important for the theory, which is dz f equals 0. I'll write it this way because then it's kind of easy to see what the solution of this is. But we can rewrite this as z d squared plus d. 0. So in a second, I'll defer this for a second, but in a second you'll see the relation of dz minus nd equals 1. So this will be an incredibly important relation that we'll see in just a second, which you probably might already know where it's coming from. But if we apply that relation here, we get exactly zd squared plus df equals 0. Now, here the solutions are there on an appropriate set as before by firstly, the constant functions clearly satisfy this. Yeah, because it gets killed by this first d. But now, if we look at it, if we read it in a kind of different way, we're saying that d of this should be 0. So we're saying that zd of f should be a constant function. In other words, d of f should be z inverse times the constant. Okay. And so that leads you to guess that log might be a solution. And indeed, you plug in log, we get d of log is 1 over z, times z is 1, d is 0. So this is solution spanned by 1, so the constant function. And log. And again, I look at my leading coefficient, I see this has a problem at 0, and so I know that you know, I'm going to have issues with my solutions over 0. And note here that the constant section, that this solution extends over 0, and this one does not. And so that's kind of interesting. Yeah, note. One extends over 0. So now I just want to discuss a very important topic called monodromy. So what is the idea here? So here I choose a basis of my solutions, and I have an m-dimensional vector space. So I've chosen this basis. Now, so basically what I want to say is that we get a representation rho from phi1, the fundamental group of C, take away the zeros of AM to the LM. And this is called the monodromy routine. And how do we get this? So somehow I'll explain it the way that everybody always explains it, but I feel like you actually need to, like somehow monodromy is one of these things that you just need to keep thinking about as a mathematician. And the more you think about it, the clearer it gets. Okay? But I'll just give the same old explanation. Okay, so apologies for not saying anything like it. So we have a loop around. And we want to associate to this loop a map from, and so we want to associate this loop a matrix. And we do this as follows. We choose a basis of solutions here. And now, on another open set, we can choose another basis of solutions. But notice that on this overlap, we have two different bases of solutions here. And so these are related by a matrix. And it's very important here that this, like if you're used to algebraic geometry, this matrix would be, for example, a matrix of polynomials. But here, we have solutions which are, we have a finite dimensional vector space of solutions. So if two solutions agree in a tiny little area, then they agree on the whole open set. That's brilliant. So we actually get, you get so we have a basis here, we can extend it to a basis here, we can extend it to a basis here, etc. We can extend it all the way around, and then at the end of the day, we get a new basis here, i.e. in the element of the matrix, and this is called the monodromy representation. So let's just work out what the monodromy representations are in these examples. And I would strongly emphasize, if this monodromy business is new to you, please think about it. So here, the monodromy representation rho is just 1.
Really, maybe the useful word instead of the analytic continuation.
Yeah, exactly. Yeah. Yeah, so we take our solutions, we analytic, continue, analytic, continue, analytic, continue, analytic, continue, all the way back. And now we have a new set of solutions, which are not necessarily our solutions, but are related by a matrix. That solution is our monodromy. So here, our solution is global, our monodromy matrix. I'm a little bit worried that Jim has the wrong point of view on monodromy, but I guess she's sleeping. This is one, we have a global solution. This is interesting. What happens here? So this is kind of an easy one to think about. The way that I think about this one is that I choose, so my basis here, I choose to be the square root function that takes 1 to 1, the good old square root function that we know and love. And then we start going around our circle. And what is happening here is that, so here my square root is 1. I come around here, what's my square root? It's this point here. I come around here, what's my square root? This point here. So the square root is lagging halfway behind as I roll around the circle. And then I roll all the way around here, and now my square root is -1. So in other words, I've sent my square root function to its negative. So here the monodromy is -1. This one is a little bit trickier to think about, but here's one way of thinking about it. What's the monodromy here? So if this is C, and this is C, here I can consider the exponential method. It is a globally defined function. And then I can think, so here I have 1. And then I can think about which points map to 1. And I get 0, 2 pi I. And now a branch of log is a local section of this map. So a branch of log is a map back. And somehow, now that I'm at the board, I can't convince myself of this, so I just have to write down the answer. Apologies.
Isn't this the definition for complex bounded log? Like,
Yeah, I mean, I'm happy with this picture, but somehow when I was preparing this, when I stared at this picture, it was clear to me that the monodromy. So basically, if I take log and then I go around once.
Yeah, that loop goes to the line which goes from 0 to 2 pi I. So the value
Ah, perfect.
you're just
Yeah.
lifting the loop.
So this loop here is what Alex is saying. Goes to the line. It goes from 0 to 2 pi I when I lift it up into this universal cover. And so what that tells me is that log transforms into log plus 2 pi I. Okay, so I get my same log function back, except now I've added a constant, 2 pi I times the constant function times 1. So that tells me that my monodromy matrix is 1, 1, and like that. So this is what happens to my constant function, and this is what happens to the log. And please, like, I really think that this is one of the more like important basic things to think about in this course. So if the computation of monodromy is not clear, please think about it again and again and again. So, what have I explained so far? We've looked at solutions of linear differential equations on C, done a few examples, and seen that we get this one over here. So, question. Rho what do you reckon? Sorry?
Yeah, it does.
Yeah. That's what trivial.
They're both trivial, but also the equations are kind of.
Well, X. Definitely doesn't seem like one.
So it's like, if it is a trivial equation, then at first it never say it could be another equation.
So I think that, you know, I definitely can't argue with Chris's reasoning that these two are different and these two are the same. Yeah. So the first answer is no. You know, like, and in some sense, like at the end of the day, Harish is right. But at the moment, the answer is no. You know, D minus 1 of F is not theorem. Okay? And also, like, it's very hard to imagine that these are somehow the same differential equation because, like, X looks very, very different to a constant function. Yeah?
Sorry, just if you had any differential equation where the AM is constant, then you might be trivial.
Yes.
So okay, so it's really just a ton of it.
Yeah, there's a ton of it. Yeah. How would you think about this, like, given the fact that you know that at some point we're going to have to digest some algebraic geometry? So X is scary, that's fine, yeah. It doesn't look very algebraic. But there's a kind of better answer, I think. Does somebody just want to say something random?
You look at infinity instead of
Exactly, yeah. So this guy, so X, you know, looks very, very bad at infinity. It has an essential singularity at infinity. And this is, so X is bad at infinity. And the technical term that we will meet in some weeks is not regular singularity. And, you know, and Alex's point is that whenever I have a differential equation that has a leading term that's a constant function, you know, I'll get something with no monodromy, but at infinity it will have very bad value. And it's good to keep that example in mind, because what it tells you is that, like, if you're allowed one of these things, one of these non-regular singularities, you can put an enormous amount of complexity in it. Okay? And so one of the things that we do in D modules is just kind of forget about non-regular singularity D modules and pretend that the world is manageable, but actually there's this enormous complexity in non-regular singularities. That's its first answer. Second answer is the second no, but for a kind of different reason. So when we look at this, what you can convince yourself of is this equation, f equals 0. And so I'm just telling you that this is a fact. So this equation has monodromy. So I'll make a short break in a second and then we'll actually see why. I'm saying this equation has monodromy x 2 pi I lambda. Okay. So I haven't told you why, but you can believe this because when I plug in lambda equals a half, this is true. I get out -1. And this implies that z delta minus lambda prime has same monodromy if lambda minus lambda prime is in Z. Now, we'll make a break, but after the break, I'll explain that these lead to the same D-module. So I'll explain after the break what a D-module is, but the kind of moral that I want to get across after the break is that a basis to a vector space is kind of analogous to PDE to a D-module. So I'll make this precise in a second, but one of the lovely things that D-modules allow you to do is study systems of linear PDE in a kind of coordinate independent manner. So there's many differential equations that one can write down that are the same. However, you know, how does one clarify that they're the same? They're actually the same D-module. So let's make a short break and then we will continue. So I realize this is pretty early for a break. I thought this would be 45 minutes.
You're looking at this in pattern, can I ask a question?
Sure.
When you say they lead to the same D model, is that when lambda and lambda prime are integer, or that leading to lambda?
No, so lambda and lambda prime will lead to the same D module if and only if their difference is an integer. And maybe, yeah, just for a little bit more padding, at the end of the day, so this is kind of
Geordie.
Yeah.
One thing that might be helpful is to say that you think of the solution as Z to the power of lambda.
That's super helpful. So the solution of this D module is kind of Z to the lambda. And you know, this makes, if we do ZD of this, we get exactly lambda times itself. And so this formal expression can be understood as the solution of this. It also makes sense on a normal disjoint from reality, and then it makes sense with monodromies as given. And then C, the with enough adjectives, so this, the adjectives are holonomic regular singularities. And the verse sheets the answer turns out to be yes. And this is the famous thing called the Riemann constants. And maybe just because I have a tiny bit of time, I can explain some history of this. So, you know, Riemann was this absolutely extraordinary mathematician. And one of the things that he proved is that if I have a simply connected Riemann surface, then it is either P1, C, or the hyperbolic plane. This is the Riemann uniformization. Okay. So, you know, if I take inside C, I take some crazy, you know, region, there is some analytic map that takes that onto the hyperbolic plane, or the unit disk inside hyperbolic space. Totally amazing theorem. And Riemann was somehow incredibly influenced by Harish-Chandra. So I don't know how many people I've given this raid to, but so at the time, so Riemann was a student of Gauss in Göttingen, and then went to Berlin. And in Berlin, he at that stage there was a school of people like Weierstrass and stuff who were great at manipulating massive power systems. They were the masters of kind of algebraic manipulation of power systems. And somehow, like their mathematical world was big formulas and big numbers. And Harish-Chandra had a much softer approach to things. He was like, how can I understand a function in the softest possible way? And this is the way that Riemann approached his uniformization theory. He said, okay, we just want, you know, we want to search for this function. We're going to formulate a solution of some differential equation in a very soft way, and then argue some unicity of solution. And somehow this philosophy that Riemann introduced was incredibly influential on many people, including on Hilbert. And when Hilbert gave his famous list of problems, he asked the question, if I take C and I remove 100 points and I specify some crazy monotony, can I find a system of Fuchsian differential equations that will realize this monotony? And he said, it's really lovely in the problem statement, he says something like, you know, although Riemann didn't state it, it's very clear that he had these kind of problems in mind. And I think it is clear that Riemann had these kind of problems in mind, but it's a very lovely kind of recasting of this problem. So this became the Riemann problem. Like how can you understand differential equations through the line? And that's why it's called that today. And you know, and now we understand. It's really funny. Like the solution of the Riemann-Hilbert problem on C now is basically trivial with all this machinery. So D is I think university in this course when it's not in the right category to know differential operators. So at the moment I'll just say differential operators on C. This is differential. And so this is the subalgebra inside of endomorphisms of CX. This is polynomial functions on C generated by P and multiplication by oops. And this turned out to be isomorphic to the Weil algebra. So this is the non-commutative algebra generated by Z and Z, Z and D, modulate the relation with the commutator of Z and D. Okay, so this is the non-commutative algebra of the two variables, and I assert this relation with the commutator of D and Z is 1. And where does this relation come from? From the Leibniz rule, we know that this is dz times f plus z times df. And so this is the F. And so what this says is that the commutator of multiplication of D and the multiplication. So I just want to go through this explicitly once because I think maybe some people will not see it. So this another way of writing this is D Z F minus Z D F with F. But another way of writing this is that we have two operators here. We have D and Z, and their commutator, D and Z, operating on F, which is just the identity operator of F.
Geordie, is D good dot F equal to F?
So, sorry, what? I mean, yeah, what I meant by that is this whole expression is equal to F.
Sorry, F is equal to Z.
He means D of Z.
Oh, sorry, yeah.
It's like this operator.
Yeah. Yeah.
Okay, and so that's what, like, obviously, if you've done this stuff before, then maybe not so obvious, like, at the very beginning, that's where this relation comes from. This is saying that as endomorphisms here, the commutator of differentiation and multiplication with Z is the identity, is one. And the other important point, so this is an algebra, and for any U in C, for any open set, D acts on analytic functions. So this guy acts by multiplication by Z, this guy acts by negotiation. And so I just want to emphasize this thing again, which is that although this is an algebraic theory, whenever we apply solution functions and some functors, we should consider analytic functions. So now consider a differential operator theory. So this relation means that things inside these rings look exactly like. So they look like some A, I, Z, D, I. Okay. So the general thing in this free algebra looks like a whole lot of Z's and a whole lot of D's and a whole lot of more Z's. But now I can apply this commutator thing to move all my Z's to the left-hand side, so I get something like what I had before. And I can consider the multiplication on the right side is differential operator, and then D1. And now, for any U, let's write OU and for analytic functions on U. Then we get, so by left axis of, so I want to form, so firstly, this is the D module, and I want to form from D modules into this. So form as D modules from D1, D2 to OU. So left axis of form says that so I'm forming to something here, so this maps to forms from D to that something. So form D to OU then goes to home. So this is as modules over D. And now, whenever I have a read home as A modules from A to something, just recovers that. Okay. Here I get OU then. And this map turns out to be action by my differential operator. And so this is exactly those F in OUN such that P. So in other words, this is solutions of P on U. So here I'm using lefty factors. Okay, so that's very nice. So this is the way I can write down some D mod D times P. And homing from this D module into analytic functions on U recovers the solutions of that differential operator on U. And the model, which I'm hoping is kind of moderately convincing now, and will become more convincing in 10 minutes, is that D mod DP is a coordinate free description of differential equation P. So if you'd like another discussion of this by someone that's much better at the subject than me, so the very first pages of this book, you have the same thing. So just to convince you of this kind of coordinate-free description thing, I just want to revisit the D module that we consider, sorry, the differential equation we considered over D module. So we have the following thing. And this is the setting of the first exercise. So suppose lambda is not in Z. So in the notes on the internet it says lambda is in Z. Thanks for Alan pointing out this typo. We consider m lambda, which is D mod D times the same equation again. This is the left D module. And so if you think about D, it has a basis consisting, D has a basis consisting of things of the form Z to the I times partial to the J. But now I'm imposing this relation, which basically means that I can get rid of any ZD. So what I'm left with, so m lambda looks like the following. So it has, so what I'm going to write down is a vector space basis. M lambda. And then I'll describe how D and Z act. So this is going to be the action of Z. And this is somehow easy. You have to divide, multiply 1 by Z, I get Z. If I multiply Z by Z, I get Z squared, etc. And now, if I multiply Z here on this guy, I can use my relation and see that that's the same thing as just lambda times 1. And now it's a little exercise to see that here I get lambda minus 1. And I'm sure and then I can do the action of so this goes down 1, 1. And now if I multiply dz, d by z, I can again use my commutation relation to get this lambda plus 1. And the exercise is descriptive, just check this description. And now the second part of the exercise is, that's part A. So it is roughly what I'm saying here. I have this D module, I have a vector space basis of it, and this is my operators, how my Z and my delta pack. Now, the second part is that M lambda is simple. As a deal. Can anyone say why this looks readable?
So you need your large value.
Yeah. So, like, I'll give you the bad argument that's not bad. That's not an argument. So imagine that I start in any one of these spaces. Then it's clear that I can just move around and get any other basis there. So I can get anywhere in one. Therefore it's simple. But now a little bit more argument, I need to say that if I start with any linear combination, it's non-zero, I can still get it. Okay. But that's why I think it's now, this is the kind of punchline, which is that, so this implies that M lambda is generated by any non-zero V inside M lambda. So any non-zero vector inside the space is going to generate. And so what that tells me is that M lambda is isomorphic as a D module to M modulating annihilator of any subthing. And this gives me another kind of differential equation. Of M lambda. So for example, this guy, like, let's just take this vector Z. So the annihilator of Z. So the annihilator in the module is everything that kills that. And you can see that if I apply Z D minus lambda plus 1, that this is going to kill it. Okay, so if I go, so I start at Z, and then I go, I apply delta, I get back to lambda plus 1 minus Z. And so this thing certainly kills it, and hence the left diagonal generated by that also kills it. And so this tells me that like M lambda is isomorphic to M lambda plus 1. Because this is exactly the description of M lambda. And yeah,
you sort of know that your idea is the principle when you do it,
no.
and they won't.
I think in like maybe there's something special in the one mentioned situation, but in general, absolutely not.
Okay.
But somehow, like, you know, just by choosing this innocent next vector, we get another differential equation. But if we have some complicated vector here, we get another differential equation that will describe an isomorphism. So, like, once you take this point of view of the, so you know, like every choice of generating vector leads me to a differential. They're all the same differential equation in the end of the like they're all an equivalent differential equation. So like that's why I'm trying to say basis is to vector space as D modulo into as differential equation. Okay. So just a very brief expectation management. So when I first met this subject, I thought, oh, this is some like revolutionary new way of looking at linear PDE. But there are many problems just on C which are extremely hard. So just a simple example of this. Imagine that you just write down one of those P that I started out the lecture. Yeah, just an innocent looking degree M differential equation on C. Linear ODE. There is no algorithm, no known algorithm to compute the monodromy of such a system in general. And like there is enormous complexity on C. You know, for example, Harini likes to study this Palinode-6 equation. You know, it's just a particular equation on C which has occupied people for the last, I don't know, 90 years or something. Yeah. So, but what I would say that D modules give you is some very useful way of discussing very complicated systems in high dimension. Well, no, sorry, kind of systems that are difficult because they're very high dimensional, not because of some kind of intrinsic difficulty in the differential. So very kind of global, soft approach to differential things.
Masud points out that it is worthwhile to note that M lambda is of rank 1 as a module, which is kind of clear from the picture.
Say again?
Masud points out that M lambda is of rank 1 as a module, that may be worthwhile to note. Or,
but does it really?
It's a semi-halfway question, I guess.
Yeah, it's not clear what that means.
Maybe it's related to if you have like if you have an n-ordered differential equation and then that's a linear equation but an n-bias matrices, and the rank of that those matrices have some restriction. No?
Yeah, maybe. I mean, yeah, I'm not quite sure what this means by that comment, but maybe you can.
Yeah.
Maybe it's like it's one thing that's important to notice is that this is a module over polynomial ring fundamental, and it's not finitely generated. Okay, infinitely far down. And you know, you can think we'll meet things like characteristic cycles and stuff. So what about implementation? So this is meant to be the kind of first introduction, so this is a little bit outside of what. But I just want to finish off today with some sketch and a connection with representation. So we take SL2.
So Geordie, just when you say not finally generated, you mean as what? Like, you know, you just showed that as a D mod.
Yeah, so it's finitely generated over D, but it's not finitely generated as a module over polynomial ring in Z.
Yeah. So it's actually generated over D by one element and freely, right?
No, it's not free over D. It has a very interesting annihilator. That's very important.
Oh, right.
Yeah, it's very much not free over D. Yeah, free D modules are kind of very boring.
Mm-hmm.
So SL2C represents 2 by 2 matrices. So it's C times 0, 0, 1, 0 plus C times 1, 0, minus 1 plus C times 0, 1, 0, 0. And this is called F, this is called H, this is called E in the time immemorial tradition. And H equals to E, H F. I'm going to check these commutation relations, and U of SL2 is the enveloping. So I hope you've seen what a Lie algebra is before. So a Lie algebra has a Lie bracket, and this is the Lie bracket in this case. And if you have a Lie algebra, there's a universal associative algebra associated to it called the enveloping algebra, which has the same representation theory as the Lie algebra. And it's often useful to think in terms of this enveloping algebra. And now we have a nice exercise, which is the following kind of rather arbitrary looking assignment. So extends to a homomorphism. So I want to first phrase this in a kind of like rabbit out of the hat type of way, and then I'll try to explain a little bit, a little bit of time where it comes. But this is the rabbit out of the hat explanation. I just write down 3 differential operators, and then you can compute, and hopefully I didn't make a mistake, that, for example, if I take the commutator of 2ZD and F, I get -2 times D. So in order to solve this exercise, there's just 3 things you need to check, namely that the image under these relations hold, and then this will automatically extend. Okay. So this is already kind of remarkable. So what it tells you is that any D mods gives us a representation of S of T. Okay. So this is remarkable. And what's even more remarkable is the close to it. Maybe for some people in the audience, it's useful to know that there's certain people in the world, and I'm one of them, that really cares deeply about representations of this and related basis. And somehow this fact that out of any D module, which looks like a kind of object from a different universe, we can produce a representation of this algebra is very simple. This is close to an equivalence. So let me explain that. So this, I'm getting into the realm where I want you to do some work. So this is slowly merging into an exercise. So OK1, this is the structure figure. So I'm hoping that coming to this course you have some algebraic geometry, but if you think of, so if you do not, then you probably know that P1 is glued out of C, and C under the map Z goes to Z inverse. And now there's some object which, when I put in an open set, spits out the polynomial functions on that open set, and this is called the structure sheet P1. So this is an object that takes in sets and spits out commutative algebra. So this is a sheet of commutative algebra. DP1, so I told you what differential operators on A1 were. And now it turns out you can build a sheaf with differential operators contiguous. So this is the sheaf of algebraic differential operators. So this is the sheaf of non-commutative parts. Okay, so I think that in the next lecture we'll see more detail on this, but a crucial computation in algebraic geometry is what is the sheaf associated. So I have an affine scheme, an affine variety. So the functions on that affine variety is given by a commutative ring A. What are the functions on a principal open corresponding to a function f? And the answer turns out to be A with f inverted. And now it turns out that differential operators on that will just be differential operators on A, where I now invert f in the same way. So that's what we'll see.
So Geordie, should we think of m lambda? Is it reasonable to think of it as a connection on a line bundle on P1 minus some points, like on a rank, like in that sense, sort of rank 1?
Absolutely, yeah. So this is, if we invert Z, this immediately becomes coherent sheaf, M lambda. So this turns out to be a connection on something on C star extended in some interesting way over 0. And the fact that it's extended over 0 is where this non-coherence comes from. Yes, I agree, Masood. Okay, so now we have localization theorem, P1. Yeah, and I think that it's incredibly useful to think about D modules as being coherent sheaves with connection, and I'm hoping that that point of view will become clearer in a couple of weeks. It's a very important thing. So localization theorem. So this is in case of P1. And in my opinion, even in this case of P1, this is already an incredibly beautiful fact about the world. So I should have said that inside here there's a capacity, which is EF plus FE from half E squared. And this generates the center. So here I have this big infinite dimensional non-commutative algebra. It has a center, and it turns out the center in this particular case of SL2 is generated by a single element, and that element is called the as in.
You know what, Steve?
Apologies. So the localization theorem says two things. One thing is it says that this, before I said that we had this map to differential operators on P1, then actually this map kind of has a true incarnation as well as the map, the global sections on P1 of differential. So this is the sheaf on P1, and I can look at its global sections, and it turns out that this is the same thing as SL2 mod C. And maybe another part of this exercise is the check that C matches to 0. This particular product of these differential operators matches to 0. And 2, so this will this is in some sense like a little bit too hard given what I've said this week, but it'll make much more sense in the weeks to come. Global sections determined. The equivalence. Categories between PP11. So this is modules over this sheet of rings, sheets and modules over the sheet of rings. So modules over global sections, but this turns out to be U of the section. Let's see. What? And the moral two. So one of the first things that we learn in algebraic geometry is that P1 has no global regular functions. So if I have a function, the polynomial is both the polynomial in Z and the polynomial in Z inverse consequence. And so what that tells you is that global functions on P1 are not useful, or global functions on projective varieties are not useful. But it turns out that certain algebraic varieties have this miraculous fact that there's enough global differential operators. So what moral 2 says, so the moral of 2 is that P1 is like an outline variety. Or D1 is. And this is what people call D affinity. Okay, so the challenge questions, so I'll stop and then we'll start engaging in some challenge questions. So which admit and 2 prove part 1. Part 1. So show the global sections of differential operators in P1 are the same thing as these three, are generated by these three dudes right there. Yeah, and so remember, so the exercises previously, and I would encourage you to try to do the exercises previously and then reach the challenge questions in other words. So the earlier exercises should be much easier, and then these are the and you know, of course, feel free to leave anyone at any time. So this is one exercise, which is really just a complication, and I hope I didn't make a mistake. And then there was this exercise showing that this big module is simple.